So today we're going to look at something called a power series, okay? And we're going to look at representing functions by series by doing this, by looking at what we're going to talk about today, okay? So we have this sigma notation, okay, n equals 0 to infinity of x to the n. So if we expand this by putting 0 in for n and then 1 in, we would get this series 1 plus x squared plus x cubed plus dot, 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 all the way to n, right? And then plus we would keep going forever, okay? Taking a look at this, what are we multiplying by each time to go from one to the next? Well, we're multiplying by x. So 1 times x is x times x would give us x squared times x would give us x cubed. So this is like a geometric series, okay? And so what do we know about a geometric series? Well, it's gonna converge depending on what your r value is, right? So in this case, what our r is, that's the thing that we're multiplying by each time. It's x. Whoops, and I didn't mean to write x cubed. I did not mean to write that. Okay, so it should be x. All right, so we're multiplying by x each time. That means our r is equal to x. All right, well, under certain circumstances, okay, we know we can find the sum for a geometric series, right? So we know it's the first term, right, which in this case would be 1 over, okay, and then it would be 1 minus our r value. In this case, it would be x. So what this series is representing, okay, is this function right here, okay? Now, a few things. This is only true. Like this series is only equal to this based on what our r is, right? What are our restrictions? Well, it's the absolute value of x has to be less than 1 for a geometric series, right? Your r has to be less than, the absolute value of r has to be less than 1. So that means if we expand this, what does the absolute value of x less than 1 mean? It means -1 is less than x is less than 1. Okay, so that what this means is that this series is identical to this function, okay, for all x values between -1 and 1. All right, so these are going to be the same. Now, if we stop it, like if we stop this at some, they're not. All right, so it has to be the fact that it goes on forever is the case that this is going to be the function. Okay, so that means we can start to write some functions. Okay, so like I'm just going to go backwards with this. So if we start with f of x, something like this, f of x is equal to 1 over 1, whoops, 1 minus x. I started right, x minus 1. Okay, so 1 minus x. We know that we can write this as a series 1 plus x squared plus x cubed plus dot, dot, dot plus x to the nth power. So that's some power out. And then plus dot, 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 continue forever. And then we could write this. Okay, so we recognize this as like being very, very similar to the formula for the sum of a geometric series. And that's what allows us to realize, oh, it's just a geometric series, right? With our r being 1 and our first term being 1, or our r being x and our first term being 1. So that means this is equal to sigma n equals 0 to infinity of x to the n power with, once again, -1 is less than x, which is less than 1, or, okay, -1 to 1. That's in inequality notation, and this is in interval notation. So what it is this right here is called the interval of convergence. And you're going to hear that term. So that's the interval in which this function and the series converges, okay? They're the same for that, for only those values, okay? All right, so now let's switch, and we're going to now talk about what is the definition of a power series. So this this is what the definition of a power series is. It's any series, okay, that has powers of x. So x squared, x cubed, and so on up to x to the n. The c sub 0 and c sub 1 are like our coefficients, okay? And you can think of these as, because these are going to be like functions, all right? You can think of these this one would be called centered at x equals 0. All right, so you'll understand that a little bit more after when I talk about this next one. Okay, so this one is x minus a. So this one's going to be centered at x equals a. So what this does is x minus a is shifts the convergence over to the right a units. And so that's why it's going to, or shift it right or left, depending on what the value of a is. Okay. Because if a was negative, right, this becomes x plus a, which causes it to shift to the left. And then you're centered, it'd be centered at x equals negative a. Okay. All right. So again, you have these coefficients, right? And you have these powers of x minus whatever the value of a is. Okay. We say that c sub n of x minus a to the n, that's called the nth term. And again, we say that it's this series would be centered at a. Okay. And this is called a power series when you have x to integer powers of 1, 2, 3, and so on. All right. Okay. So let's do a little bit more with this. So for this next sigma notation in form of a series, right? It's n equals 0, sigma to infinity of negative x to the n. Okay. So if we raise this to the 0th power, that would give us 1. And then if we put 1 in here, that would give me negative x, so minus x. And then if we put 2 in here, we would get plus x squared. And then we put 3 in, we'd have negative x cubed. If we put 4 in, we'd get positive x to the 4th, and so on. And then the next one, notice it's alternating, right? So it'd be minus x to the 5th, and then plus dot, 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 and then plus. And so we could write this as negative x to the n power plus dot, dot, dot. So we start taking a look at this. Okay, so how can I go from one term to the next? Well, what am I doing? Well, I'm actually multiplying by negative x each time, right? So every time I'm multiplying by negative x to get the next term. Okay, so what does that mean? That means my r is negative x. All right. Now, one way you could also write this, all right, is you could write this as negative 1 to the n and then x to the n. That's an alternative way of writing this. Okay. So we should recognize, okay, this is just like a geometric series. All right. And so what's the interval of convergence? Well, it's this r value, right? It has to be less than the absolute value of it has to be less than 1. So what we have is the absolute value of my r, which in this case is negative x, has to be less than 1. That means negative 1 is less than negative x, which is less than 1. And then what I could do is I could multiply, this left, middle, and right by negative 1. Now, when that happens, the direction of these inequalities change. So this is going to be 1 is greater than x, which is greater than negative 1. Or a better way of saying this is negative 1 is less than x is less than 1. So negative 1 less than x less than 1. Okay, which means our interval of convergence is negative 1 to 1. Okay, so let's take a look at this. All right, so our series is 1 minus x plus x squared minus x cubed plus, and then dot, 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 plus, we always have to put this nth one in, negative x to the n power plus dot, dot, dot is equal to, okay, so since this is just like a geometric series, it would be the first term, which is 1. The sum of this would be 1 over 1 minus our r value, and our r value is negative x, right? So this would be 1 over 1 minus x. So this particular series becomes 1 over 1 plus x. Now, what all this means is f of x, okay, we could call f of x this new function, which is 1 over 1 plus x. And then what we could do is write this in sigma notation. It would be n equals 0 to infinity of negative x to the n power. And then this would be our our interval of convergence. So our interval of convergence is negative 1, which is less than x, which is less than 1, or negative 1 to 1. Okay, so like this all relates to, our convergence tests and everything else that we've been learning about. All right. And so here we go. This function. Okay. So these are the same, but under restrictions. And this is the restriction that what we put in for X has to be between -1 and 1 for this to be true. Okay. And that's really important. Like this only works. That's why we called the interval of convergence. It only works on this interval. Outside that, doesn't converge. Okay. All right. Let's do another one of these. So looking at this series, n equals 0 to infinity of cosine to the nth power of X. Okay. So if we put 0 in here, so that'd be cosine of X to the 0, and that would be 1. And then we put 1 in, so that'd be n would be 1, so that'd be plus cosine of X. If we put 2 in, that'd be plus cosine squared X plus cosine cubed X plus ... and this just keeps going. And so we need to write this plus cosine to the nth power of X plus ... And so this keeps going and going up, going, right? So if you notice, okay, to go from one term to the next, we're multiplying, right? We're multiplying by cosine X. So that means my R is cosine of X. Because we know this R, okay, that means we could rewrite this sum, right? As long as there's restrictions on what cosine could be, but the sum would be equal to our first term, which is 1, over 1 minus our R, which is cosine of X. So now what's our interval of convergence, right? Because that's what we're talking about here, okay? So our R is cosine X. So this is only going to work when the absolute value of cosine of X, the absolute value of cosine of X is less than 1. That means -1 is less than cosine of X, which is less than 1, okay? All right, so what we have now is a new function, okay? So our new function is f of X is equal to 1 over 1 minus cosine of X. Well, we know that can be written as a series. So sigma n equals 0 to infinity of cosine raised to the nth power of X, which is the same as this series that expanded out, right? 1 plus cosine X plus cosine squared X plus cosine cubed X plus ... plus cosine to the nth power of X plus ... And we need the ... to mean it keeps going, okay? And then the interval of convergence would be between -1 and 1 again. Now, there are some restrictions on this, okay? So what we have here is -1 is less than cosine X, which is less than 1. That's our interval of convergence. Even though it's not written as an interval notation, that's still called the interval of convergence, okay? Okay, so this is going to work whenever cosine X is between -1 and 1. And if you think about the graph of cosine, it goes between -1 and 1, and occasionally it is -1. It does reach -1, and it does reach +1, okay? So, okay, so we've got to add a little bit of wording with this, okay? So this geometric series, this geometric series would converge for all X, okay, except multiples, well, here, except, okay, and what would they be? Well, X couldn't be, okay, so where cosine X is either -1 or 1 is at 0 pi or 0, 1 pi, so plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, right? That's everywhere where cosine, the graph of cosine X, is either reaching -1 or +1. So it can't be any of these. So really this means because cosine X is pretty much always between -1 and 1, except for at these specific ones, we're going to say this geometric series would converge for all X, except X equals K times pi, where k is an integer. So these are all integer values. So where k is an integer. So if our x value for this function was like, say, pi over 2, okay, so it's not one of these, right? So that means this function can be rewritten as a series, all right? And that's what this all boils down to, okay? This can be written as a series, this functions. And so it's kind of weird. We're going to develop different types of functions, and we're going to come up with series for those functions, all right? And then maybe something's really hard to integrate, but the series is easy to integrate. So that's why this is going to be important, or differentiate. And we're going to come up, you're going to see, we're going to come up with different functions doing this technique I'm showing you. All right. So for this third example, okay, we're going to use the series in the function f of x that it represents to find a power series for f prime of x, the derivative. Okay. So we have this function, right? F of x is equal to 1 over 1 minus x. We know from earlier that we can write it in sigma notation like this. We know the radius of convergence is between -1 and 1. And so this is the function written in expanded series form, right? Okay. So if we take the derivative of our function, and our function is 1 over 1 minus x. So I'm going to write this as d over dx of 1 over 1 minus x. Okay. So if we take the derivative of this function, right? That must, since this function and this series are the same for this interval of convergence, all right, then that means we could take the derivative term by term of this. So let me show you how we do that. Okay, so this is going to be the derivative with respect to x of 1 plus x squared plus x cubed plus x to the 4th. Sometimes, okay, so I'm going to tell you, sometimes it's really nice to start to see, like, okay, how do I write the formula for this? Okay. And then plus x to the 5th. And that's why sometimes I'll go out pretty far, not just like the first couple of them. So plus dot, 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 and then plus x to the nth plus dot, dot, dot. Okay. And I'm going to close my bracket. So it's impossible to take the derivative of each one. We're going to try to come up with an x to the n term. Okay. So d over dx. Okay. So I'm going to rewrite this. So instead of trying to apply the quotient rule on this, I could rewrite this as 1 minus x to the -1 and just apply the chain rule to it. So this is I'm going to rewrite this as 1 minus x to the -1 power. And this is equivalent to, and then I'm going to just write this again, d dx of, and then 1 plus x squared plus x cubed plus x to the 4th plus x to the 5th plus dot, 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 plus x to the n plus dot, dot, dot. Okay, so when we go to take the derivative of this, all right, the power comes down, right? So that'd be -1 times 1 minus x. We got to subtract 1 from the power, so that'd be -2. And now we got to take the derivative of this inside function, which would be -1, right? Okay, and then, all right, so that must be equivalent to the derivative of each of these, right? So the derivative of 1 is 0. The derivative of x is 1. The derivative of x squared is 2x plus 3x squared plus 4x cubed plus 5x to the 4th plus, and then dot, 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 plus, and this one, okay, so what would we have to do to take the derivative of x to the n? We'd have to bring the power down. So it'd be n times x to the n minus 1 power, and then plus dot, dot, dot. Okay. All right. So rewriting this with this -1 times -1 would be +1. So this becomes 1 over 1 minus x squared. And we know this is equal to 1 plus 2x plus 3x squared plus 4x cubed plus 5x to the 4th plus dot, 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 plus n times x to the n minus 1 power. Whoops, n minus 1. Why did I write plus? Fix that. N minus 1 power, and then plus dot, dot, dot. Okay. Now, one thing. Okay. So whatever our series, our original function, the interval of convergence, our derivative is only going to work on that same interval of convergence, okay? So I'm going to write this: since f of x converges for -1 less than x less than 1, so does f prime of x. Okay, so what does all this mean? Okay, so this, we start with f of x, right? So what does this mean? This means f prime of x is equivalent to 1 over 1 minus x squared, which is equivalent to sigma. And right here, by realizing this is my formula that I'm going to generate for my sigma notation, okay, it's going to be n times x raised to the n minus 1 power, okay, and then down here we're going to write n equals, okay, so what do we want it to start with, right? What do we do? What value do we want to start with? Well, okay, we want to start with this one, right? This was actually the first derivative, right? It was 0. We didn't write it here, but we wrote it, right? So we actually want to start at 0, because then we'll get the right term. If we put 1 in here, we would be starting with 1 right here, and that wouldn't quite line up right, okay, with what we have here, okay? So then we're going to go to infinity here. All right, and we know our interval of convergence from this right up here. Our interval of convergence is -1 less than x less than 1. All right, so that's a way of now writing derivatives as a series. Like, kind of crazy, right? Kind of crazy. All right, so let me slide my notes up and talk about term-by-term differentiation a little bit more. So if we have a function that can be written as one of these power series, right, and we know it converges, and in this case, right, if we look at this, what we're multiplying from term to term to term is our r would be equal to x minus a, okay? And so it's going to converge for the absolute value of x minus a less than some r value, okay? So that's going to change depending on the problem that we have, all right? And so then we know if this series converges, then the series, which is this one, and this is obtained. This one's going to be obtained by taking the derivative of this power series. It's always going to take on this form, okay? Then we know that we can do it, and it's called term-by-term differentiation. So we're taking each term of the series and differentiating that and coming up with a brand new series. That's what we just did, okay? And then this is saying, okay, it converges, then the new series converges under the same interval of convergence. That's what this is saying. This r, so I should tell you, this r is called the radius of convergence. We'll talk about that more as we get more into this unit. Okay. All right. All right. So we just did differentiation, but you could also do some other things. Okay, like term by term integration. All right. So we're going to look at that next. So we talked about like integrating a function that's written as a power series, and we can do term by term differentiation, but we can also do term by term integration. So we want to come up with a series. We're going to use the series and the function f of x that it represents to find this power series. Now, this is from example 1 that we did earlier, okay, that f of x is equal to 1 over 1 plus x, all right, and we can write this as -1 to the n, x to the n. In example 1, this was just negative x in parentheses raised to the n power. So both of them are equivalent, all right? And then this is the series in expanded form. That's going to be helpful, okay? So we want to change. Now realize all of these x values are going to become t values, right? And even this is going to be t, which means all of these are going to be t values, okay? So if we take the integral of this function, so from 0 to x of this function, which is 1 over 1 plus t dt, that's equal to the integral from 0 to x of, and so it becomes 1 minus t plus t squared minus t cubed plus t to the 4th minus t to the 5th plus, and then dot, 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 plus, and then -1 to the n power, t to the n power, plus, dot, 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 close the parenthesis, and then we have to have a dt. Okay. So if you could do this by integration by substitution, but right here, okay, this function actually becomes, if we integrate it, so I'm going to not do that, just go right to the answer. This is, if we integrate this, this is the natural logarithm function. So natural log of the absolute value of 1 plus t. And then we want to evaluate that from 0 to x. Okay, so now what we're going to do is term by term integration. So this is going to equal, I'm going to put a bracket here. Okay, this does get a little bit of cumbersome, and you'll see why in a minute. Okay, so this first term becomes t, and then minus this one becomes t squared over 2, and then plus this one becomes t cubed divided by 3 minus t to the 4th over 4 plus t to the 5th over 5 minus t to the 6th. So this minus t to the 6th is coming from this t to the 5th, right? Over 6. And then plus dot, dot, dot. All right. And then plus, and it would be -1 to the n power times t to the n plus 1 power, right? Because we have to add 1 to the power. And then we got to divide that by n plus 1 plus dot, dot, dot. And then we're going to evaluate this from 0 to x. So this is where it gets like cumbersome, because we're going to have to put x into this antiderivative, right? And then minus 0 putting it into the antiderivative, okay? So it's equivalent to this one, right? So this, if we put x in for our t right here, right? This becomes the natural log of the absolute value of 1 plus x minus the natural log of the absolute value of 1 plus 0, because we're going to put 0 in for t, right? So that would just be the natural log of the absolute value of 1, okay? And that's equal to, all right? All right, so now we're going to put all our x's in wherever we see t's, right? And then we're going to, and then minus, and we're going to put zeros in wherever we see t. Well, every single term has t in it, right? So that means if we put 0 in, the whole thing's going to be 0, right? So basically all we have to do is put the x in. So this is going to become, this is equal to x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 plus x to the 5th over 5 minus x to the 6th over 6 plus dot, dot, dot plus -1 to the nth x to the n plus 1 all over n plus 1 plus dot, dot, dot. So we got to write the plus dot, dot, dot. You have to write that because that's what's showing that it's going forever. It's never stopping, okay? All right, so right here, natural log of 1, we should realize that's the same as natural log of e to the 0. So this is 0 right here. So this whole function becomes natural log of the absolute value of 1 plus x. And that function can be written as a series, right? And in sigma notation, this is where this comes in really handy, okay? This is the formula that we put into sigma notation. So it's going to be sigma n equals 0 to infinity, and it's going to be -1 to the n x to the n plus 1 power all over n plus 1. And that's how these denominators are going up by 1, because the next number we put in, we're going to add 1 to it, right? And so that's why these denominators are going up. And this is true, okay, for all right, and because our interval of convergence is -1 to 1, so is this one. So -1 less than x less than 1, okay? So either you differentiate or you integrate. The series that you get from doing that has the same interval of convergence, okay? And so this is called term by term integration, okay? And I know you're not going to understand like completely how are we going to use this. You're going to see, but you're starting to see like this is important. Like sometimes functions are really, really hard to integrate, but you can rewrite those functions as a series, a power series or some type of series, And then that allows you to easily integrate it. But you have to know, okay, they are the same, but only under these conditions they're the same. Those conditions are called the interval of convergence. It only works for these x's, okay? All right, so let's look at a couple more problems how we could use this idea. So this is kind of an exploration that we're going to kind of do together, okay? So given that this function 1 over 1 minus x can be represented by this power series, right? And we know the interval of convergence is -1 to 1, right? So this looks like the sum of a geometric series, right? And then this is the expanded series, all right? How can we take this one and create this one, right? Now, we've already seen this one, so that might help, okay? But how do we use this one to create new ones? Like, how could we create 1 over 1 minus x squared? We could do that, okay? But realize this is kind of looking like, and this is the trick to it, is this is kind of looking like the sum of the geometric series, right? So is this one, but we're missing the minus, right? Because it needs to be minus right here. Well, guess what? We can change our x to make that work, all right? So the idea behind this is we want to write 1 over 1 minus negative x. Okay, so now it matches this, right? So where we see x here, right? What the thing that's x here is actually negative x in this one. So we rewrite it and we can put everywhere we see this negative x, we can put it everywhere we see these x's up here on the series for this one, right? Because basically what we did is we got this one to match this one, okay? So that means this is equal to, and we'd have 1 plus, and it would be, we're going to put a negative x in there because that's what our value is, right? It's negative x. Basically, we're kind of using a formula, okay? And then plus negative x squared plus, and then it would be negative x cubed plus negative x to the, whoops, I put a plus. Sometimes my hand just doesn't do what I want it to do, right? Okay, so plus negative x to the 4th plus dot, 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 plus, we want the nth one, right? And so that would be negative x raised to the nth, and then plus dot, dot, dot to mean it goes forever. All right, cleaning this up a little bit, what we have here is 1 minus x minus, sorry, not minus, plus x squared, because this one would be positive x squared. This is going to be minus x cubed. And this would be plus x to the 4th. And then plus dot, 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 plus, and we could rewrite this one as -1 to the nth power, x to the nth power, plus dot, dot, dot. Okay, so that gives me a way of writing this. What is my r value? Well, it's -1, right? Or sorry, it's negative x. So this winds up being sigma n equals 0 to infinity of -1 to the nth power, x to the nth power, right? And so again, our what we're multiplying to go from one term to the next is this negative x, right? Our r is negative x. And what do we know about r? R has to be between -1 and 1, right? So, or the absolute value of r, which in this case is negative x, has to be less than 1, which means -1 has to be less than negative x, which has to be less than 1. If I multiply all three by -1, that makes 1. And then we've got to change the direction of the inequality, which is greater than x, which is going to be greater than -1, or -1 is less than x less than 1, right? So what we did is we found the power series, right? Oh, all right. And it's represented on this interval -1 to 1. Okay. So we have 1 over 1 plus x, right? 1 over 1 plus x is equivalent to sigma n equals 0 to infinity of -1 to the nth power, x to the nth power, and it's on -1 to 1 by this right over here. All right. I think anything else I need to say about this? I don't think so. All right. One thing, okay, so one thing, it's really like, I would always kind of step back and take a double check and just make sure this we're starting at the right value that will give us 1. So if we put 0 in here, right? -1 to the 0 power, that's positive, and then x to the 0 is 1. So this would be 1 times 1. Yeah, so the first term works. Okay, what if we put 1 in here? If we put 1 in for n, that makes this -1, and then x to the first, which is x, so negative x. Yes, it's working, right? I would check like the first 3. So then we put 0 in, we put 1 in. Let's try 2. So if we put 2 in, that'd be -1 squared. That'd be +1 and x squared. So positive x squared. Yes, that's what we're getting, right? So it's alternating signs like we want it to at the right spot, okay? And we're getting the powers of x that we want to, all right? So I would always just step back and just make sure you did it right, okay? All right. So let's build from that, okay? So we can take that function and do something to it and create another function. So that's what we're going to do next. So basically what we have here is x divided by 1 plus x, right? Which is really this one. And this is what we're going to have to recognize is this one is this same one, but we're multiplying by x, okay? And that's exactly what we're going to do. So we know that x times, and this one is really 1 over 1 minus negative x, all right? That's 1 plus x, right? So if we multiply by x, that is actually, right? That's the same function, right? So let me put equals here. So x over 1 plus x could be written like this, all right? Which means this could be written as x times, and then we have a series for this, right? That's actually what we just got up above, right? So this series, the expanded form is 1 minus x plus x squared minus x cubed plus x to the 4th minus x to the 5th plus ... plus, and then we had negative x raised to the n power, right? Plus ... Okay, so what does all this mean? This means x over 1 plus x is equivalent to, and now what I'm going to do is I'm going to distribute this x with each of them. So this becomes x minus x squared plus x cubed minus x to the 4th plus x to the 5th minus x to the 6th plus ... plus, and really I would write this as -1 to the n power, right? And then x to the n times x plus ... Okay, so this one right here is -1 to the n and x to the n, and then I'm multiplying by this x. This x came from this distributing of the x, okay? Plus ... Okay, so that means x over 1 plus x could be written as x minus x squared plus x cubed minus x to the 4th plus x to the 5th minus x to the 6th plus ... And then we could write this plus -1 to the n. And then we have x to the n times x. Well, there's an exponent of 1 right here. So, right, so we're going to add these exponents. So this becomes x to the n plus 1 power. And then plus, we can't forget this, plus ... because it has to go forever. Okay, so that means this function x over 1 plus x is equal to sigma n equals 0 to infinity of -1 to the n x to the n plus 1 power. And you can't see it. Sorry. All right, so I'm sliding it up so you can see it. All right, so x over 1 plus x can be written in sigma notation, n equals 0 to infinity of -1 to the n times x to the n plus 1 power. Okay, so once again, right, what are we multiplying by each time, right? To go from 1 to the next is negative x. So once again, the absolute value of negative x has to be less than 1. And we've done this several times now, right? So we know that this always comes out to be -1 is less than x is less than 1. So this is true on the value, the interval -1 to 1. So this is going to work between -1 and 1. So this function can we replace with this series only, I want to stress this, only between -1 and 1, and it has to go into infinity for this to work. All right. All right, so that's how you do this. Okay, so this is the conclusion of this part of the video. This is the first part of this, and then we're going to continue with this tomorrow with another video. All right.